Does somebody want to sum up for us how we go about finding the midpoint of a line segment, just in your own words? Come on in, George. How do I go about doing that, James? Yeah, we average the x coordinates, we average the y coordinates, and those are our two coordinates, okay? And in a normal problem, like example 8, I think, was where I gave you the two endpoints. I said, hey, what's the midpoint? That's easy peasy. This one is a little bit different in that I do what? What have I done, Reed?
I just found out what number
All right, so yeah, I've given the midpoint, and I've asked you for the end points. Now, Reed has approached this problem in the proper way. You know, he has said pretty much what our midpoint formula says, which is that if I add these two values together and cut that in half, I should get that value right there. All right. And so if I say -2 plus x divided by 2, right, that should equal that number 1 right there. And then similarly, we could say that -5 plus y, when divided by 2, should average out to equal that value, which also happens to be 1. Okay. Now we can work out these two equations quite simply. We can multiply both sides by 2 and add, in this case, 5. So y equals 7. And over here, in this case, times 2, add 2, x equals what? X equals 4. And we get our end point. Okay. Now, another way of working this would be to say, well, you know what? Let me graph this out. -2, -5. I go 2 to the left, 5 down. Right? And then 1, 1. I go up 1 and to the right 1. There's my midpoint. There's my end point. And to think, okay, well, this line segment is going to extend in that same direction. You know, I'm going from A, I'm going up and to the right to get to M. Now, this conjures up notions of what that we learned about regarding lines back in the first semester. Slope, yeah. This conjures up ideas of, well, what was my vertical change compared to my horizontal change, or my rise compared to my run? So you tell me, how much do I rise up? How much do I run over? Well, when we count it, 1, 2, 3, 4, 5, 6, and then 1, 2, 3, we should be able to count up again 6, and again 3. Up 6 over 3, up 6 over 3 to get to B. And so I had some students that will oftentimes think, well, okay, let me just add 6 to this and add 3 to that. And we certainly get 4, 7 that way as well. So it matters not to me. If you're a visual learner, you can do it that way. It takes a little bit extra time, and sometimes it doesn't always work out, you know, nice and neat. But the formulas certainly do work out nice and neat. So that's midpoint formula with a little twist. Sometimes you'll see that, you know, like on an ACT kind of test. Any questions about distance or midpoint formula for that matter? All right. I'm going to introduce, we've been talking about Pythagorean Theorem in 11.1. That's what this section is all about, is Pythagoras and some applications. I'm going to introduce a couple of specific examples of triangles, of right triangles. And I call these our special triangles. Okay, whoops, where do we go? There we go. All right, so this first triangle is called a 30, 60, 90 degree triangle. All right, write that triangle down, draw it up. It's a 30, 60, 90 degree triangle. You will encounter this next year in geometry. You will encounter it the following year in trigonometry. You will encounter it the following year after that in either pre-calculus or calculus. Okay. This triangle is very special. That's why we call it a special triangle. Its mommy thinks it's special too. But it's got interior angles always add up to what? 180. For a triangle, the sum of the three interior angles is always going to be 180. So that's, you know, 30 and 60 makes 90, and 90 makes 180. It's a right triangle, so what do we have working for us in our favor? What do we know about right triangles? The Pythagorean Theorem. Yeah, that's the context in which we've been working, right? So if I know, yes, I know the angles add up to 180. We just said that. If I got 30 and 60 and 90, if I know this is a right triangle, then I know one leg squared plus one leg squared equals hypotenuse squared. So it says use the Pythagorean Theorem here in example 10 to solve for the missing leg in terms of x. So what is that missing leg? That missing leg is my question mark. So question mark squared plus x squared equals 2x squared, right? One leg squared plus one leg squared equals hypotenuse squared. And be careful when you're squaring a monomial like 2x. You got to do what? You got to square the 2 and the x. All right. So what do we wind up with down here? We got question mark squared plus x squared equals 4x squared. So I end up, when I subtract 1x squared, I get 3x squared equals question mark squared. And then, Will Edwards, what do I do to undo a square? We're going to take the square root of both sides. I've run out of room, so I'll scooch over here. We got question mark equals. Now, taking the square root of 3, I can't really do anything there, right? So I'm just going to have square root of 3. And then square root of x squared, we would normally say is absolute value of x, but because x is the side of a triangle here, it wouldn't make sense in that context to consider it being a plus or a minus, a negative, for example. So we're going to be left with x square root of 3. So I'm going to erase that. I'm going to write x square root of 3. And I want you guys to memorize that triangle right there. That's called your 30, 60, 90 degree triangle. Okay? Now, what's nice about a triangle, and let's just take time out just for a second, you kind of catch up maybe with some of the algebra, or you're making a special emphasis in your notes about this triangle. The word similar is different from the word congruent. Okay, and you'll learn this next year in geometry, but the word similar is different in that two triangles can be similar like this. Right? Are those two triangles congruent? No. Their sides don't equal each other. They are not identical. That's what congruent means. It means it's the same exact. What do you think similar means? Read.
Same shape, different size.
Same shape, different sides. Okay, okay. Let's see if we can expound upon that, because I could draw another right triangle up here that's not similar to these two. Joey, add a little bit to that. Okay. Anybody else? What? Oh, Jack, go ahead. Ooh, yeah, that's what I was fixing to go for. What we know about similar triangles is that their angles are congruent. Their angle, and I just threw up a 3, 4, 5 so I could show the proportionality of their sides, right? What did I do, Grove, to get from the little triangle to the big triangle regarding the sides?
You multiplied everything by 2.
Yeah, we just scaled up. We sized it up by 2. Okay. And so these two triangles are similar, and similar triangles have their corresponding angles are all congruent. Okay. Their corresponding angles are all the same. Okay. So a 30, 60, 90 degree triangle, let me clear out these sides now. And similarly, we'll say this one's 30, this one's 60. Well, that means that this one's 30 and that this one is 60. So I've got, again, similar triangles. Bless you. And so whereas maybe this side is 1, 2, square root of 3, maybe this side is 5, 10. Get fancy here. Oh, come on, OneNote. Yeah, now we're cooking. All right. So maybe it's whatever scale factor you want it to be. You know? So like over here, 1 times 2, and 1 times square root of 3. Here it's 5 times 2, and 5 times the square root of 3. Here it's x times 2, and x times the square root of 3. They're all proportional. They're all similar triangles, okay? And we can have our scale factor be whatever we want it to be, okay? The way that you'll learn the triangle in geometry is right here. The way that you'll learn about the triangle in trigonometry is right here. We scale it down to where the shortest side is just equal to 1, and you'll use it in your trig class that way. Okay, so just bear in mind that a special triangle like this 30, 60, 90-degree triangle, it fits in the Pythagorean theorem, right? Because 1 leg squared plus 1 leg squared equals hypotenuse squared, regardless of which scaled up version you're dealing with. They're all three fitting in with Pythagoras, okay? So that's our 30, 60, 90-degree triangle. Similarly, this is our last triangle to consider. I've got one over here that's written up. And you could actually go ahead and classify this one a little bit differently. Nate, what do you know, just from looking at this picture right here, what do you know about this triangle? Anything that you want? All right, very good. It's a right triangle, okay? Joe, what else do you know about this triangle? Just from the picture, not doing any calculations. The two legs are the same. Do we have a vocab word for that? Joey? Paul? Isosceles. So I like how Nate said it's a right triangle, and Paul said it's an isosceles. It's called an isosceles right triangle. Now, fellas, what do we know regarding the relationship between an angle and its opposite side? For instance, what's the biggest side of that triangle? The hypotenuse. How do you know that? Because it's crossing the biggest angle. Okay. Well, what do you know, therefore, about the other two angles? Why are they the same? Because the two sides are the same. So, like, you quickly identify the hypotenuse as the biggest side, right? Well, what's the next biggest side? And you look at it and you think, well, wait a minute, the next biggest side, there's not a next biggest side. Those two are the same length. So there's not a next biggest angle then. 90 degrees is the biggest angle. These two angles are the same. Therefore, Luke, what must their measure be? Very good. Very good. So an isosceles right triangle is what we call a 45, 90 degree triangle. This is the second of our two special triangles. Okay? So an isosceles right triangle, it fits all the things that we know. It has 180 degrees as the sum of the interior angles. It's going to also fit in with the Pythagorean theorem. Okay? So I can use my Pythagorean theorem. And George, you want to set that up for me? Use, again, do like we did earlier. Use the X and the question mark there. Set up Pythagoras for us. Beautiful. X squared plus X squared equals question mark squared. Couldn't have said it better myself. All right, and we just want to get the question mark by itself. Okay, we want to get our unknown hypotenuse by itself. I'm going to consolidate these two over here. Alex, what does that add up to? Try again. 1 apple plus 1 apple equals 2 apples. So 1x squared plus 1x squared equals, attaboy, much better, 2x squared. And then if I want to get, Mossy, if I want to get the question mark by itself, what do I do to both sides? They're already being squared. Good, attaboy, square root both sides. So we'll square root the right. We know that cancels it out, gets my question mark by itself. And then we'll square root the left over here. Now, square root of 2, I can't do anything with it. Sorry, just square root of 2. What about square root of x squared? Just x. And again, in this context, we're not going to worry about absolute value because x is the side of a triangle, which isn't going to be negative in this context. So x squared of 2 winds up being my hypotenuse. So x square root of 2. All right, so now that we've solved it out, come over here to the side where we were doing all that scale factor business. Where's my green triangles? There we go. All right, and let me draw out. Here we go. Here's a 45, 45, 90. And we'll say 1, 1, 1 square root of 2. Or maybe I want to say, let's scale it up. Maybe I want to say 3, 3, 3 square root of 2. Or maybe I want to get real crazy and, let me scoot these down. Maybe I want to go big or go home, as they say. Again, here's 45, 45, 90. Okay, and maybe I want to say x square root of 2, whatever you want that scale factor to be, right? So like in trigonometry, you'll learn it as 1, 1, 1 radical 2. That's sort of the base model, if you will. And then you can upsize it accordingly. 3, 3, 3 square root of 2, 5, 5, 5 square root of 2, 10, 10, 10 square root of 2, a million, a million, a million square root of 2, whatever. And so what this does is this allows us to have two very special triangles with some special angles, like 45 degrees and 30 degrees and 60 degrees are all, when you consider in trigonometry, one full rotation split up. Here's 30 degrees. Here's 60 degrees. And of course, we know 90 degrees right there. And you keep on going around and you can cut up a circle into all of these little parts. How many parts is that? 9 parts, I guess. No, 12 parts. You can cut up into 12 parts with 30 degrees being your increments. Or you could have, like the pizza. If anybody ever, we had a good pizza Friday night. Y'all ever go to Milano's? Anybody ever been to a Milano's? It's like New York style pizza. It's real good. But they cut up pizza into 8 pieces. You guys knew that, right? Well, each time they're cutting it up, they're making it at a 45-degree angle. Okay, so like you could cut up a rotation or a revolution into 8 congruent parts that way. But guys, these are special triangles. Memorize them as soon as humanly possible. You'll see them for the next 4 or 5 years. Okay? And again, just get a little exercise with Pythagoras. So any questions that you've got over Pythagorean Theorem, distance formula, midpoint formula, or special triangles? Anything you want to ask about? All right, then. We're going to completely, teetotally shift gears now. I mean, this is like non sequitur of non sequiturs. We've been talking about Pythagoras, and now we're going to leave that behind, and we're going to talk about what I have in my hand right here. What do I have in my hand? I've got some dice. These are dice from an establishment called Sam's Town. When I started working here, the department chair left me some of his dice. I think he likes to go to Sam's Town. So he left me like 20 of these casino dice. And he said, these are helpful for when you're talking about things like probability and whatnot. And so I've been using them with this next little lesson here. I rolled a die. I just rolled a 3. If I were to ask you, what are the chances or what's the probability that I roll that 3? Do you know how to calculate that real quick and real easy? Quentin, you shot that hand up pretty quick. All right, very good. And there's only one way to roll a 3. Excellent. Again, kudos. I couldn't have said it better myself. So when we talk about probability, it's a good illustration right there of what he just said. If I ask you, hey, what's the probability that I roll a 3? And you think, how many ways is there for me to roll a 3? Well, there's only one. And how many ways is there for me to roll anything? Okay, there's 1, 2, 3, 4, 5, 6 unique faces on this cube. I guess there's a probability of 1 over 6, or 1/6. I have different dice, though. I got another die that is not a 6-sided die, but it is a 10-sided die. You ever seen a 10-sided die? Have I used this in this class before? I don't know if I have either. Its digits are 0 through 9. Okay, so that's 10 digits. That's 10 faces. Now what's the probability that I roll a 3? Okay, you're not going to believe it. I didn't roll a 3. Paul, what's the probability now?
1 in 10.
Very good, very good. All right, so with just these 2 simple little rolls of a die, we have illustrated the definition of probability in its simplest form. Okay, I want you to write down that the probability of, and I know there's a bunch going on. This is a busy page right here. Just get this part down. The probability of an event occurring. If somebody says, hey, what's the probability that such and such occurs? What they're really asking you for is a ratio. They are asking you for a ratio comparing the number of ways that your event could occur divided by the number of ways that any event could occur. Okay? Now, here's where it gets a little complicated. If I wanted to roll both of these dice, if I wanted to roll my 10-sided die and my 6-sided die, and I said, all right, now what's the probability? Hold your horses. You ain't even think I know what I'm going to ask. What do you think I was going to ask, James? Close. I was going to ask, what's the probability that I roll at least 1 3? Okay. Now that gets a little bit tougher. I didn't do it, did I? I rolled an 8 and a 2. Okay, so I don't want to go into that question just yet. I think that'd be putting the cart before the horse. But can you see where, like, just with the added little wrinkle, all of a sudden the problem becomes a little bit more challenging, right? It was easy when it was a plain little 6-sided die. Hey, how many ways is there for me to roll a 3? How many ways is there for me to roll anything? So the probability of an event, make sure you got your definition written down. The probability of an event, let's just call that event E. The number of ways that E could occur divided by the number of ways that anything could occur. Okay, so like my little micro example here of rolling a 2 on this one, we said was 1 over 6, because the probability of rolling a 2 is the same as the probability of rolling a 3 on a fair 6-sided die, right? All right, let's talk about probability in general. Probability is always between 0 and 1. The answer to any probability question in the history of probability questions has always been and will always be somewhere between 0 and 1. Something with a probability of 0 is not going to happen, period. Something with a probability of 1 is absolutely going to happen, period. The vast majority of events, however, occur somewhere between those two, right? Like I might say, today I am going to coach baseball. Probability equals 1. Well, not true. What if I got violently ill and had to go home all of a sudden? You know, I ain't coaching baseball today. You might say, I'm going to drive to St. Louis school today. Well, you might get out in the parking lot and, your car might be out of gas and you might be stuck. Okay, so I don't want you to think that there aren't events that have a probability of 0 or that have a probability of 1, but in the real world, probability is a vast majority of the time is between 0 and 1. And we can represent probabilities in 3 ways: fractions, percentages, or decimals. Good, Jack. Fractions, percentages, or decimals. Okay, and it really, I don't have a particular favorite. Sometimes it's nice to say probability of 1/6. Do I really want the decimal version of 1/6? Do I really want the percentage of 1/6? No, 1/6 is fine. I'm happy with 1/6. You know, James. You're thinking ratios? Yes, you could do that, but in probability we don't do that way. Good question. Good question. All right. Here's the problem. Here's the issue. Here's the struggle. And I hope to help you with this struggle over the next couple lessons. We stink at counting. We stink at counting. You might think you're a good counter. I used to think that I was a good counter. Okay? But trust me, we stink at counting. Here's why. We think counting is just a simple matter of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, ... Continuing on, like we learned when we were little kids. But counting is actually more challenging than that. I will demonstrate. Could you, if I gave you a minute even to think about this, could you tell me the number of handshakes that would occur if every single person in this room right now shook hands exactly once with every other single person in this room? Could you count the number of handshakes? I'm going to go ahead and let the cat out of the bag. you're not going to tell me the correct answer. Okay? Do you know why? Because you stink at counting. And that's okay. I love you guys. I'm not trying to hurt your feelings. Mama, he told me I stink at counting. All right? And I love it. Some of you guys I see in the back, y'all are just counting away. Go ahead, Quinn. Not 260. Thank you. Good try. How many guys are in here, by the way? Did you count? 22. All right. The way that we get better at counting is we learn some basics. And the first basic I've got up there on the screen in purple. It's called the fundamental principle of counting. And if you want to get your handshakes question right, pay attention to this. The fundamental principle of counting says that if you have a couple of events that you want to occur, let's just start with a couple. It could be however many you want. If you want to count the number of ways that a couple of things could both occur at the same time. So maybe I've got a die, a six-sided die, and I got a fair two-sided coin to flip, okay? And I want to count the number of ways that maybe I land on heads and I land on a 4, okay? The number of ways that two events could occur conjoined at the same time, right, is the number of ways the first event could occur times the number of ways the second event could occur. So in other words, like how many, let's just simplify to my little coin flip / die roll. How many possible outcomes are there for that experiment? There are 12. Very good. Because there's 2 ways the coin could flip, and there's 6 ways the die could roll. So there's 12 ways that event could occur overall. Drew. 400 and what? 4. How'd you get it, Drew? All right. How many people are in this room? 22. All right. Let's say that George is the first person. George is not going to shake hands with himself. So George would have how many handshakes? 21 handshakes. Okay. And how many handshakes is Nate going to have? He's going to have 20. How many handshakes is Candiato going to have? And so on and so forth, right? So you get my picture, and some of y'all might have got. I don't know. It's very rare that I get somebody that actually knows. I don't even know what the answer is to that question, but I use that as a point to illustrate. It's harder than we think to correctly count things. It's harder than we think. So what do? Yes, I said learn the basics, learn a principle, and then also I want to look for ways to help me visualize the counting process. Okay? Like, for example, let's just start here with this orange question, and we'll be out of time today. It says, how many unique outcomes are there for 3 coin flips? So in other words, I got my little fair two-sided coin here. I'm going to flip it. There's 1. I'm going to flip it. There's 2. I'm going to flip it, and there's 3. How many ways could that experiment occur? What do you think, James? There are 8 ways that little experiment could occur. Okay? Now, the way that I visualize that is I think about the first coin flip, and I think, well, there's only 2 possible outcomes. And then I think, well, the second coin flip, there's 2 possible outcomes. And the third coin flip, there's 2 possible outcomes. And I want all 3 coin flips to occur. Therefore, I use my fundamental principle of counting, and I multiply 2 times 2 times 2, and I get 8. So there are 8 ways that experiment could occur. Okay? And we'll talk about brute force tomorrow, because brute force is going to come into our discussion quite a bit. Have y'all ever studied probability? Anybody ever done a little bit of this? Some of you guys have? Nice. All right, well, thank you so much, guys. I hope you enjoy the rest of your day. I will see you tomorrow. We'll talk a little bit more about probability. In the meantime, live Jesus in our hearts. All right. Thanks, guys. Have a great day. I have not seen one. Sorry, Paul. Bye. Have a great day.